Hi there, physical geographers. So we're going to go over a couple of things today. We're going to finish talking about landforms made by running water, and we're going to talk about the coast and how the coast is created. Landforms along the coast are created because of like from the ocean. And then you will be ready for your midterm on Thursday. Your midterm is going to be, I sent you all an email detailing midterms and lectures and stuff like that for the rest of the semester, but your midterm is going to be short answer. And I know that not everybody loves short answer, but unfortunately, that's what we're going to have to do. And I'm going to ask you a couple of questions about like the main concepts of what we've done since our first midterm. The study guide that's online is still the study guide that you need to know. It's still going to help you prepare, but you're going to have a full 24 hours to finish your midterm. So you can go back and look at lecture slides, you can go back and look at notes or your textbook or whatever while you're answering those questions. And so those questions will be to explain some of the basic concepts of stuff that we've gone over. And we're looking at like a paragraph of explanation for each question. Okay? And don't worry, there's not going to be 75 questions, 75 paragraphs to write. I'll just ask a few questions that will incorporate the major themes that we've discussed. Okay, so if you remember last Thursday, we were discussing streams, and we had talked about braided channels, we talked about alluvium, we had talked about aggradation. That's the stream is basically eroding, right? It's removing material from the landscape, and then it is depositing that material. The aggradation part is the deposited material. So this is where we left off the other day. A couple of landforms that are created from running water. So there's the channel, of course, and there's the floodplains we talked about. There's the braided channels we talked about. But if you're looking at, let's say, the American Southwest, this is an area that is basically high and flat. You all know the joke that goes along with that. But high and flat, it's a plateau. It was pushed up from tectonic activity into a higher elevation than sea level. And what happens if you don't have a volcanic chain like the Sierra Nevada or something like that, so that you have these little points of volcanoes, if you have something like a plateau that's created from compression, where the lithosphere gets pushed up into elevation, well, now water and wind are going to come along and they're going to break down that landscape. They're going to etch into, carve into, erode into this landscape. And depending on how that's done and what the climate is like around that area, that's going to create a different kind of landscape. Like we've talked about earlier in class, you've got peaks, you've got ravines, you've got rills. Those are all different landscapes that are created, or different landscape features that are created. So here are from water eroding. So here are a couple more. We've got a pinnacle. So first, let's take a plateau. A plateau is big and high and flat. The Colorado Plateau is in Colorado, but it's also Arizona. It's also in New Mexico. It's part of Nevada. We're talking about a gigantic high elevation piece of the American Southwest. And that is a pretty dry part of the of North America. You've got, that's later in the semester when we talk about climates. And I think I've mentioned this before. That's in a latitude where you have descending dry air, and that's going to hit all through 20 to 40 degrees north and south of the equator. So the climate plus the lithosphere, those two things working together is how we're going to get our unique landscape. So a plateau is giant, big, flat, and high. And you have water that comes along. You have particularly dry air because it's high up in elevation. And also this is in the true desert region of the world, 20 to 40 degrees north and south of the equator. So what happens is the water comes in and it erodes. Now it can erode, and we've talked about canyons and how canyons are created. It can erode, but basically a canyon, if you can see, is eroding into the landscape of the plateau. But eventually that plateau can be broken away so that instead of having mostly plateau with a little bit of eroded canyon, you could have entire plains that are created. So this plateau has been eroded away, or you reach the end of a plateau. But let's just imagine this plateau has been eroded away, and what we have left is flat, lower land and flat highland. So a plateau is big, a mesa, like the one that City College is on, is smaller, but again it's high and flat. And then a butte is even smaller than a mesa. And a pinnacle is even smaller than that. That's basically if this butte were to break away and just this one little piece was left standing. So plateau big, mesa smaller but still high and flat, butte even smaller, still high and flat, and then pinnacle, just a little tiny like point that's still left. And underneath the mesa, you're going to get something like the Badlands. The Badlands are, we'll go over this when we get to the climate, but basically air, when it goes up and down in elevation, it condenses, which we've talked about. So let's say that the air down here is warm, so it's going to be all stretched out. The air parcel is going to be all stretched out, and it's going to rise up, right? And as it rises up in elevation, it condenses and it gets smaller. So when air goes up and down in elevation, not only does it change size, but it also changes how much moisture it has. When it condenses and gets small, it squeezes its moisture out. So let's say that you have air that rises up over a plateau and dries out. But now that air is smaller and tighter, so gravity pulls it back down. And when that gravity pulls it back down, it's going to heat up again. We call that adiabatic heating and cooling, and we'll get to that much more when we get to climate. But that adiabatic heating, when air has dried out because it's gone up in elevation, and then it gets pulled back down by gravity, now what you have is air that's going to heat up again because it's going down in elevation, but it's dry. And if that air continues to descend and descend into sometimes places that are lower than sea level, like in Death Valley, now it's going to, as it descends into an elevation that's even lower than sea level, it's going to dry out and heat up and dry out and heat up, and that can create something like the Badlands right here. And these Badlands are especially dry places that you're going to see in areas like the American Southwest, in Death Valley. Okay, so here's the American Southwest once again. We've got a plateau, big, mesa, smaller, butte, even smaller in this picture. Well, this would be a pinnacle basically. Basically, these are all landforms that are high and flat, and they just get smaller and smaller and smaller. So from the plateau to the mesa to the butte to the pinnacle. Okay, don't worry about this. Our Badlands, like I said, that's extensive tracts of land that have been heavily eroded. They are not very cultivatable. There's not a lot of water. There is a lot of eroded rock. And once again, when we get into soil, we'll figure out the balance between eroded rock and biomass that is needed to create soil that can support plant life. But Badlands is where you have basically a lot of eroded rock, and it's so dry that not a lot lives, so you don't have a whole lot of biomass. And then a playa, if anybody's ever been to Burning Man, that takes place on what people call a playa, or if you have been to Isla Vista, or if you speak Spanish, you know that playa means beach, right? What does playa mean? Sorry, I think playa means beach, but now I'm second guessing myself. Okay, anyway. So, a playa is an area that is going to have possibly once been a sea or an inland sea, and it's now dried up. So all of the minerals that would be in, like, let's say a sea or a lake When that water evaporates out of the lake, remember when water turns to its gas state, vapor, it leaves all its minerals behind. Uh, and when it leaves all its minerals behind, they're just going to sit in the ground right here. So when you have a playa, which used to be, maybe a lake or something like that, which all the water, the fluid evaporated out of it, you now have a place that's going to be pretty warm and pretty dry and maybe have like an accumulation of salts or something like that. And a playa is also going to be in a place that is very, very warm and very dry, which means that any water that makes its way into that playa, if you get like a storm, if you get like particularly freezing um, weather and you get a whole lot of snow or something like that, it's going to evaporate and dry quickly, which is again going to leave the minerals behind that might have been in that water, leading to an accumulation of that water, or sorry, of those minerals. So down here it says what human practices could also produce badlands. Well, um, over leaching soil in agriculture. We're increasing our desert land every year in the world by 20,000 acres because we're basically growing things and we're leaching our soil. And that's one way that we could produce badlands. Okay, so ocean currents. And we want to start talking about ocean currents because we're going to move off the land and how the land is created, landforms are created by running water, and look at how our coast is creating by by ocean water. So first, we haven't talked so much about ocean currents in this class, but and again, it's because we end this class with the climate. If we had started with the climate, then we would have talked about the Coriolis effect and how this is the equator right here. What happens is everything in the northern hemisphere, because of the Coriolis force, which will, when we get to the climate, you will understand much more of. But basically, because of what we call the Coriolis force, everything, all the wind and all the air that runs along the equator, if it's north of the equator, it goes at a clockwise, so basically the water and the air up here spins in what we call a gyre. That's a great big circular movement of either water or air, depending on what we're talking about. And it moves in a clockwise direction. If we are south of the equator, again because of the Coriolis force, the water and the air are moving in a counterclockwise, like this direction. So the gyre, the circle of water or air, is moving counterclockwise down here. And that's important. That's important when we get to climate later. It's important because we want to understand the Coriolis effect force, but it's also important because it'll have to do with why the east coast of a continent always has a warm current and why the west coast of a continent always has a cold current, and that makes a difference in microclimates, and it's very exciting, and we'll get to it later in the semester. Okay, so all you need to know for now is that ocean currents are a persistent force of water that either run clockwise or counterclockwise if you're in the northern hemisphere or in the southern hemisphere. And another big part, okay, so our ocean currents are circling around like this, if you're following my arrow. So that is the direction of that current as it moves from Alaska to California. It hits the equator because of the Coriolis force. It moves along the equator. It moves up Indonesia, East Asia, and it continues to circle. So that circulation is happening, but at the same time, there is a whole other circulation happening underneath the ocean. So at the same time, while you have, if you follow my arrow here, the ocean water is circulating around the continents. So imagine that this arrow is hitting the California coast, and then it's along the equator, and then it's hitting China, and it's coming up again, and it's circulating. But imagine this is the water. So underneath the water, there's also another circulation that's happening. So from the top of the ocean, like let's say you're sitting on a boat. If you're sitting on a boat, there is another circular movement of water that's going from the top of the ocean where you're sitting on a boat to the bottom of the ocean. So that circulation is just amazing. What that's doing is that circulation is taking nutrients from the bottom of the ocean and upwelling them, bringing them to the top where you're sitting on a boat, and then taking energy and sunlight and nutrients and just circulating them around and creating this whole nutrition system, this whole system of warm water and cold water getting dispersed, not just from the top of the ocean, like in these gyres, but so like not just along the circular movement of the ocean and the currents, but also in the movement of energy and biomass from the bottom of the ocean to the top of the ocean. So there's these two circulations happening. One, the water is moving in gigantic circles, and two, the water is going from the surface of the ocean to the bottom of the ocean, and it is moving mass and density and all kinds of stuff. Not mass and density, what am I talking about? It's moving energy and nutrients. So that's thermohaline circulation. That's cold, dense waters that make their way from down here in Antarctica and make their way up, and then they heat up along the equator, and they continue to transport warm and cold water, and then there's also the nutrients that are being circulated from the bottom of the ocean to the top of the ocean, bottom of the ocean to the top of the ocean. It's all a process. What's happening in this, once again, we'll talk about this more when we talk about climate, but this is one of the many ways that we take the energy surplus that's at the equator and we disperse that energy. So, as you all know, the sun is coming in to like the sun's energy is coming into our atmosphere, and it only hits at 23.5 degrees north and 23.5 degrees south of the equator. So there's a surplus of the sun's energy right in here, right in what we call the tropics. And there are multiple different ways that the Earth gets that energy and circulates it to the northern hemisphere and to the southern hemisphere. So what's happening is we have a surplus of energy that's coming in from the sun all around the tropics. And then we have a couple of different systems taking that surplus of energy and dispersing that heat to the very northern part of the world and the very southern part of the world. When we come back to the climate, guess who else is doing this? It's hurricanes. Hurricanes, while they are horribly destructive to us, what they do is they take a surplus of energy that accumulates in the ocean and around the tropics in August and September and basically hurls that energy from the tropics all the way up here. We'll get to that later. The energy I'm talking about right now is the sun. It's the heat of the sun. So one of the ways that the sun's energy, the heat of the sun, gets transported up here is in what we call this thermohaline circulation. It is super cool. All right. El Nino, we're going to come back to when we talk about the climate again, but it is an example, once again, of what happens when ocean circulation gets, not once again, but it's what happens when ocean circulation kind of gets messed up. So if you can see in this picture right here that there's a surplus. This red is the surplus of the sun's energy. And then up here, the water is much, much colder. And so there's this normal circulation of water that's happening where the water is moving around in this gyre and it gets heated up. And then because of the Coriolis force, it veers down, goes along the East Australian current. You get some nice heat. Look, that's the east side of a continent. A trick in geography is to know that the east side of every continent is warm. So as the Eastern Australian current disperses heat, where's my arrow? My arrow keeps disappearing, sorry. The Eastern Australian current comes down along the east coast of Australia. You've got a nice warm current happening in there. And then that current continues to come along Antarctica. It gets very, very cold. It's freezing cold down there. Penguins love it, but me not so much. And then it hits South America. It moves up along South America, so the west side of South America is getting hit with a cold current, and that cold current gets warmer and warmer, and then look, the whole thing happens again, and it continues to circulate. What happens in El Nino? So you have cold water right in here, right off of the coast of Peru and Chile and all of these countries along South America. And that cold water, just like cold air, is dense. So it's going to sink to the bottom of the ocean. Look at how my arrow just disappeared. Why does that keep happening? So that cold water is going to sink to the bottom of the ocean. That's called downwelling. And we'll come back to this later when we talk about the climate more. But that downwelling, that nutrition and cold water, they sink to the bottom. But every once in a while, and we don't know why, that downwelling gets reversed. And so instead of having this movement of nutrition in this cold water, this cold, dense water, sink to the bottom, we have this reversal. So what happens with El Nino is, for some reason, there's this warm current of water that makes its way into the normally cold water off the coast of Peru, and that warm water switches the density of the water. So now it's not cold and heavy, it's warm and light. And so now you have this reversal of the normal downwelling to upwelling. And what happens is this whole system gets affected. So just right here, there's a little bit of warm water that comes in, and that warm water means that the whole system of nutrition in cold, dense waters that's making its way down to the bottom of the ocean gets reversed. And now you have basically warm, just like warm air rises, warm water rises. So we don't know why it happens. We just know that it happens every once in a while. And as a result, now you have this warm air, or sorry, this warm water, and it basically reverses the normal cycle, the normal thermohaline cycle of this water, and it leads to a whole lot of rain here. If you've ever lived through an El Nino winter, you know that it's a very, very wet year, but it's not our normal wetness. It's not the normal wetness that comes from Alaska. It's a wetness that comes from down here, and it's not actually that great for us. We're going to come back and talk about that when we talk about the climate. But what is very, very wet for us here on the west coast of North America and the west coast of South America leads to a drought over here in Australia and in East Asia. So in their El Nino years, it means for them a whole lot of drought. For us, it means a whole lot of rain. It's a good example of how we're part of a system, that we can't just isolate one part of the world and talk about the geography there, that when something happens here, it happens all over here. So we will come back to El Nino when we talk about the climate, but in talking about thermohaline circulation, it's good to mention it. All right, so let's switch over here. Here's a quote of the day for you. I don't know if I've given this class this quote before, but this is one of my favorite quotes. You can keep your symbols of success. Just think about what those symbols of success might be, and you'll pursue your own happiness. Okay. So we have been talking about river channels and how water shapes the landscape of the land, right? But water is also shaping the coastal landscape. Water is also shaping the way our coast looks. So first, let's understand the anatomy of the ocean just a little bit. Now, I know that you all know what wind is, or at least you've experienced wind, and I know you all know what waves are, because you've probably experienced waves. But sorry, I'm trying to signal my daughter to go help my cat. Okay. So there's an anatomy of a wave, is what I'm trying to say. I know that you know what waves are, but let's really know what waves are. So the anatomy of a wave is the wavelength. The wavelength is the distance between crest and crest of a wave. So a wave happens because of wind, and we haven't talked about wind in this class yet. We'll talk about it when we get to the climate. But wind is basically wind is the sideways movement of air. That's all wind is, and it happens because there's low pressure and there's high pressure in the world. And low pressure and high pressure means that, so if you have low pressure, that means air is rising. Air has mass. So if air has mass and it rises, then other air is going to run in to fill that empty space. And that sideways movement is wind. So when wind drags along, when wind drags along the ocean, it pulls water up. And when it pulls water up, we call that waves. So the anatomy of a wave is first the wave trough, that's the low part right here. And the wavelength is between the two crests of the wave. So crest to crest, that's the length of the wave. This is the trough of the wave. This is the peak of the wave. When a wave breaks, that's when it starts to basically curl. That's when you get this, basically it's hitting a shallow part and there's drag at the bottom, and it breaks. It turns into like a cresting wave. That's what we call surf right there. Okay, so there, so there is two parts of this breaking wave, or sorry, there's not two parts of this breaking wave. There's two movements of a wave. One is in and one is out. The in is called the swash. The out is called the backwash. So that wave is getting pulled onto land because of wind. And when it hits the land, the forward movement onto the land is swash. And the backwards movement, when it gets pulled back out into the ocean, we call that backwash. Now what happens is there's a whole lot happening. For one, the water is coming in. It's transporting deposited material, it's transporting eroded material, just like what's happening with fresh water on the land with rivers and stuff like that. That river water that's eroding away the landscape also has to transport that eroded material. Well, the ocean has eroded material as well. So when that swash happens, that forward movement of the wave happens, it transports and dumps material. That material becomes the beach. And when that gets dragged back, that backwash also transports material. If you have ever left a towel on the beach and the tide has come in and your towel is gone, it was taken by the backwash. So this water comes in a zigzag. So basically it doesn't come in a straight line, straight back, straight line, straight back. It comes in so that you have swash, backwash, swash, backwash, and it creates a little zigzag. And that zigzag is the drift. It's the undercurrent, the tow that you might feel if you've ever stepped into the ocean. So if you've ever stepped into the ocean and stood like right here, you feel a little sideways movement. That sideways movement, that current, is being created by the swash and the backwash, the swash and the backwash. They basically create a sideways movement that we call littoral drift. The word littoral is a great word, rhymes with other words. My daughter got that. The littoral is the name for the unique ecosystem that is the beach. So think about it. Dry land has its own ecosystem. The ocean has its own ecosystem. But what about this area right in here? It's sometimes covered in ocean water. It's sometimes just sand. That is going to have its own adaptation of sand crabs, of the types of the ecosystem basically that adapts to the ocean water sometimes being here and the sand sometimes just being here. That is what we call the littoral zone. The littoral zone. So a littoral zone is basically the beach zone. And littoral drift is what happens right along the beach. That's if you've ever left your towel right here and the swash comes in, and then you find that it gets moved down the beach a little bit before getting taken out here. That is your littoral drift. The littoral drift is what happens right along where the swash and the backwash meet the beach. It's also called beach drift. The longshore drift is a little bit further out. So let's say that you're on a surfboard or you're sitting in like a little raft and you take it past the break of the waves. So you have the break of the waves, and in the break of the waves, the movement of swash and backwash create what we call beach drift or littoral drift. But if you go past the break of the waves, that's when you're going to get into again a current that's being created from the swash and backwash, but it's going to be much more significant in size. That's what we call the longshore current or the longshore drift. The longshore current is if, let's say, you sit on like a little raft right here, right past the break of the waves. If you just sat there and didn't row, didn't like do anything off of Ledbetter Beach, you would eventually be taken to Ventura, right? Because you would be caught in the longshore current. That longshore current is going to follow the same huge ocean gyres. So it's always going to be the same direction as those ocean gyres we just talked about. Those ocean gyres where the water that's coming along the California coast right now is coming from Alaska, and it's going to end up at the equator, and then it's going to go by China and by Japan, and then it's going to go to Alaska again, and then it's going to come back here. The longshore current anywhere, whether it's off the coast of Santa Barbara, whether it's off the coast of New York, it's going to follow those ocean gyres. That has to do with the Coriolis force. That has to do with the general direction of wind and water, depending on if you're in the northern hemisphere or the southern hemisphere. And I will explain those when we get to climate much more. So, with this movement, this littoral drift, with this longshore current, all of that swash and that swash and backwash are going to be constantly eroding away the landscape. So if you imagine that California at one point, so California is what we call an erosional coast, an erosional coast. Whereas if you look at the other side of the US, if you look at like Georgia, Savannah is a city, what am I talking about? Georgia, the Carolinas, all that part of North America, that is depositional. All of that was created from eroded, basically the Appalachian Mountains being eroded. Whereas California was created from uplift. California was created from tectonic activity that led to the North American continent being uplifted. And we talked about all of this in the last section when we talked about the lithosphere, just to remind you. So once you have, if you imagine just like a straight line of cliff, and I am simplifying this, I know, but just so you can kind of imagine, like that once upon a time this was a straight line, and it would have been a straight line of, let's say, like cliff all along a straight California. And then the earth gets to work, and here comes the ocean, and the ocean swash gets pulled in, the waves get pulled in by the wind, and they hit the side of the California coast, and they erode away material. And eventually, after a very long period of time, what we're going to get is an uneven landscape. Where this used to be a straight line, the ocean has come in and eroded and transported and deposited material all along the California coast. And I'm using California as an example, but all along any coast, basically. So what we have left of what used to be a straight line are now these points that stick out. We call those headlands. Now the reason that those points are going to stick out is because the rock is going to be stronger. Basically what eroded away here, what used to be rock right here, that rock was more vulnerable. That rock was able to be eroded away faster. And these headlands are now the remnants of what used to be a solid coastline they're still standing because their rock is more solid, basically. It's harder to erode. But now, remember when we talked about erosion and we talked about how exposure means that you're going to be more and more eroded? Now these headlands are going to be eroded faster because at first it was just the ocean coming in and eroding and like breaking away and eventually creating this entire huge gaping part of our landscape. But now this headland is getting it from like multiple sides. It's getting hit over here, it's getting hit here. This is going to be eroded away pretty fast. And I'm going to show you pictures of how that gets slowly eroded in just a minute. But what we're looking at right here is the process of erosion and deposition. So this landscape was eroded. The what used to be like just a straight line of California coast was broken down into smaller and smaller pieces, transported by the ocean, and deposited to make a little beach. So this pocket beach, this is a depositional landscape. This headland, that is an erosional landscape. If you remember, we've talked about this in class. Erosional is basically what's left after the water has worn away the rest of the material, and depositional is what happens when that eroded away material gets dumped somewhere, gets deposited somewhere. If you imagine like a river channel coming down a mountain, it's eroding. It's going to have like a sharp V-shaped channel, and it's going to be eroding and eroding. And then when it hits a valley, it's going to dump all of its eroded material. The channel of that river is going to change. The the amount of material at the bottom of that river is going to be very different. So in the same way, the ocean is constantly beating against the coast and eroding away and then depositing, eroding away and then depositing. And so this beach right here is a deposited landscape. It's a landscape that's created from deposited material. This headland is a landscape that's created by the material being broken away around it. Okay. Now our tides. A lot of people might think that this is all tides, that a wave is basically a bigger tide, but it's not. A tide is something that's different. A tide is happening from the gravitational pull of the moon. Basically the moon, which the moon got sucked into our gravitational orbit. I know sucked is not a technically correct word to use, but just imagine it gets sucked into our gravitational pull. And it spends the rest of its life, for as long as we know, just gravitating around the gravity of the Earth. So the Earth has pulled the moon in, and the moon is just spending the entirety of, since it's been the moon for the Earth, just circulating around, being pulled in by our gravity. That means a lot for the moon. The moon isn't even able to twist. We only see one side of the moon because that's how strong our gravitational pull is on the moon. Basically, the moon is trying to rotate. It's trying to do what we do. We rotate over here. It's revolving around us, but it's also trying to rotate. But the gravitational pull of the Earth is so strong that it can't even twist away and rotate. So our gravitational pull is pretty hefty. But the gravitational pull of the moon, it has its own gravitational pull. It's not nearly creating what we are doing to the moon, but it's what's creating our tides. So our tides are not quite waves. Waves are the swash and the backwash that are created by wind, but our tides, the gravitational pull of the moon, there's no D at the end of the moon, the gravitational pull of the moon basically means that that swash and that backwash end in different places on the beach, depending on the moon's relation to us here, if that makes sense. So there's a couple of different tides I'm going to go over in just a minute, but the tides don't create the wind. The tides don't create the waves. The tides just create where the break line for those waves are. So big waves like tsunamis. I showed you a video on tsunamis earlier in the semester. I'm going to post that again. But those are, if you remember, you've got an earthquake or you've got this major energy release in the ocean. And as that energy makes its way through the ocean, it creates this huge drag that leads to gigantic waves that we call tsunamis. And as we know, it can lead to like terrible, terrible consequences for us. Okay, so tides. Depending on the gravitational pull of the moon, we have different levels of our tides. So our flood tides, those are high tides. That's when you go to the beach and there's basically no beach there. That's a flood tide. A spring tide is a high, high tide. That's when you go to the beach and you can't even see the beach. It's basically just the ocean. So a flood tide, that's your high tide. A whole lot of the beach is taken over by the ocean. And the spring tide, that's the high, high tide. An ebb tide, that's a low tide. That's when you go to the beach and it smells super funky and actually not quite super funky. That's when you go to the beach and you can see tide pools and you can walk out further to the ocean. The neap tide, that's the low, low tide. That's when it starts to smell funky. That's when you get like gigantic beds of kelp just washed up and they're sitting there in the sun, and that's your that's your low, low tide. So your tidal range, while it has to do with the moon, like I said, it plays again a huge part in shaping landforms, because what the tide does is it changes where the break of the wave is. It means that the erosion and the deposition is going to be that much stronger if you have erosion coming in to if this break of the wave is happening further up the beach. Now the erosional capability of that wave has just stretched to a farther point of the beach. And if you have a low, low tide, now what's going to happen is the transportation of eroded material is going to be that much stronger back into the ocean, if that makes sense. Okay, so our coastline. I know you all know what a coastline is, but just to remind you, that's the zone, the littoral zone. That's the zone where coastal processes are happening. That's going to have its own ecosystem. Think about it. Plants and animals and everything are going to have to adapt to sometimes being covered in salty water and sometimes not. And the shoreline shifts, and that shifts between tides, basically. Okay, so just to look at our different types of erosional landforms, this looks like the California coast, right? This is somewhere like you could go to Morro Bay, you could go along the one, and you would find, once again, because California because like we talked about in the last section of class, where we have the creation of North America, basically this part of the lithosphere being pushed out because of convergent plate boundaries, we now have this rising cliff above the ocean. And then the ocean gets to work, and the ocean gets to work, and it erodes, and it transports, and it erodes, and it transports and deposits, and it creates a whole different landscape. So once upon a time, remember I talked about the pocket beach and then the headlands. Well, this used to be a headland. But what happens is the headland is now used to be the strongest part of the landform, and all of this weaker rock got eroded away. But now this stronger part of the landform is sticking out. And as it sticks out, it is getting eroded from multiple sides. And so it breaks down, and what you have left are stacks. Maybe you have a little sea arch. Eventually this is going to be eroded away, and we're going to have just a little stack right here. And eventually all this is going to be eroded away, and it's just going to be straight line. So a sea cliff, that's a rock cliff that's being weathered and eroded away by breaking waves. It's probably not going to have a really big beach. It's going to have just a short little pocket beach. A lot of it might be dominated by rocks. Basically what we see here in California. Okay. And then over here, our marine terrace, that again is something that we're going to see in California a whole lot of. You have, let's say that once upon a time, the ocean came up to here, and then you have uplift happen. And when that uplift happens, now you have this whole new landform that gets pushed up from the lithosphere and is now higher in elevation than the ocean. And so now what you have is a former sea cliff, and then you have a nice little marine terrace, and then you have the new beach right here. So the marine terrace is, it's going to be, you know, space that you don't necessarily know. Like if you're walking over it, you don't necessarily know that you're walking over what used to be under the ocean. But the difference is that there's going to be a whole accumulation of minerals that would have been in the salt water right here. There's going to be former like biomass from the ocean, like fish and everything, are going to be in the soil and in the sediment. So if you look at the California coastline, we're going to see marine terraces as well. We're going to see high flat areas. In fact, the mesa is a place you can think of as a marine terrace. If I've said before that if you went into the side of the mesa, like if you're walking along the Douglas Preserve, or you know, the area that I've talked about in class that like looks out over Hendry's Beach, that if we were to like pick up the soil along the Douglas Preserve, the Wilcox property, and analyze it, we would find fish, like old dead fish in there basically, because what we're looking at is something that used to be under the ocean that got pushed up, and now there's a new ocean line. So that's our marine terrace. And then waves, once again, tsunamis. I will repost that video of tsunamis. So then the other side of landforms, besides our erosional landforms, are our depositional landforms. And our depositional landforms are our beaches. Now, if you've noticed, California beaches are pretty small when it comes to, not necessarily when it comes to length, but when it comes to amount of space between ocean and the end of the beach, if that makes sense. So like right in here. And that's because we're on an erosional coastline. We're on a coastline that is uplifting and being like eroded away by the ocean. Okay, so let's go to the other side of the country. Let's go to the East Coast. And along the East Coast, we're going to see, and this is true on the East Coast of Australia, this is true in a lot of different places in the world. You're going to see beaches where the break of the wave and like the littoral drift happening right in here to the end of the beach is going to be very, very long. Basically, you have like way more beach than you have here in California, where we have a lot of like short beaches with marine terraces and, you know, little sea cliffs and stuff like that. So what happens on the East Coast is basically because you have material that's being deposited from the Appalachians, you have material that's being deposited from here in the ocean. What's happening is we'll have much more depositional material than erosional material. That because it's a landscape that's dominated by material that's being deposited rather than a part of a continental plate that has been uplifted, you're going to see much bigger beaches. It's going to be more depositional. Okay, so along our depositional landform, we're going to get things like lagoons, things like baymouth bars. Now, just because we live in California and it's dominated by erosional coastline and erosional landforms doesn't mean that we don't have stuff that looks like this. If you go to Pismo Beach, you have coastal dunes. If you go down to San Diego, you're going to see a landscape that looks a lot like this, like this depositional landform right in here. So what's happening, again, in an erosional coastal landform, you have more uplift happening, so that the ocean is basically actively chipping away at that uplift. Whereas here you've had more material deposited than lithosphere being uplifted. So what's happening is that depositional landscape becomes the kind of primary focus. All right, so let's look at a lagoon, for example, or let's look at right in here. So basically, you have water that's going to come in from inland, and that water, when it comes in from inland, it's going to be depositing material, and then the ocean is pushing in deposited material, And when those two meet, when you have a lot of deposited material coming from the land and a lot of deposited material coming from the ocean, and they get deposited and deposited, you're going to see these little you're going to see the appearance of a landform that's created from all this deposited material. So right in here, this is called a spit. You've probably heard of a spit before. A spit is deposited material that's now creating like a little bridge in front of an inlet. So this is a water inlet, like a beach. Like these could be headlands. Um, and here you have your pocket beach. And you have so much material that's being deposited that now there's basically a little island. That island is called a spit. When that island, when that spit, basically when that island meets the other side, that's when we call it a baymouth bar. Now you have an entire piece of deposited material that's created an island that's creating a separation between the ocean, open ocean, and now this little inlet. And we call that a lagoon. So sometimes that lagoon is going to get a whole influx of ocean water. If the tide is high, if you have a big wave, there's going to be a lot of what's out here in the ocean coming into the lagoon. Other times, this lagoon is going to see more fresh water. So you're going to see a change in consistency of salty ocean water to fresh water. We call that brackish water. Brackish water is a little bit salty, a little bit fresh. And guess what? There's an entire ecosystem that has adapted to it. Okay, so we see spits, we see baymouth bars. A lagoon is a little enclosed, salty, little bit fresh water pool of water that's now protected from the open ocean. Oh, we've got a tombolo. That's basically like a spit, except going from a headland. Remember back here? I said this is eventually going to be eroded away so that there's no more material. Well, if you look at this is that sad little stack now left all on its own. And there has been so much eroded, deposited material that you now have a little island called a tombolo. So tombolo is going between a headland and the coast, and a spit is basically working to close off and create a lagoon. And I hope you can see the difference between this and what used to be the headland. So the headland would have been part of the continent, basically. This is material that's been eroded by the ocean and dumped here. All right. These barrier islands, or back here, so like this baymouth bar, can create entire little isolated tidal inlets, mud flats, salt marshes, wetlands. Like once this area is closed off from the open ocean because of a baymouth bar, because of a little barrier island, now you have an entire ecosystem that's going to develop on its own. You're going to have plants and animals that adapt to the brackish water, the just like a little bit salty water and a little bit fresh water. You're going to have an entire ecosystem that develops because now it's in isolation. It's not in complete isolation because the ocean water still gets brought in, but it's also getting fresh water. It's not getting pounded by the ocean all the time with the waves, and it's its own ecosystem.